Hello and welcome to the third video in our series on discrete math review for Foundations of Computer Science. Our topic is relations. So we'll work through the definition in a minute, but from the outset, an intuitive way to think of relations is that they are just sets. And in particular, they're a special kind of set that contains tuples. And the idea is that the elements in the tuple are related. A tiny clerical note is that while originally this was one video, I went through and added a bunch of annotations and examples and problems, and it got kind of long, so I've split it now into parts 3a and 3b and 3c, etc. So let's take a look at how we're going to build this idea out of the concepts that we've defined already. So first we'll start with the definition. We'll say an n-ary relation, R, is a subset of some big Cartesian product with n sets in it. So it's a Cartesian product from S1 cross S2, etc., up to S sub n. So it's useful to remember here what a Cartesian product is. Remember, a Cartesian product just contains tuples, where the tuples are formed by taking one element from each of the sets that is crossed and listing them in something that looks like a tuple or a finite sequence, depending on how you want to view it, or coordinates. Right? And these tuples are the things that are related. Now, if we took the whole Cartesian product, everything would be related because the product contains all possible tuples. So we don't take the whole product, we just take a subset of it, and that's what our relation is. It's just the things that are related out of the possible things that might be related. And so just to introduce some of the terminology we use, we'll say R is a relation on this product. It's a relation on S1 cross, etc. up through Sn. And we say n is called the arity of the relation. And you should think of that as the number of things in the tuple or the number of things that are getting related by the relation. In this class, we're going to see a lot of binary relations. If all the sets are actually the same set, right? If all S1 through Sn is actually the same thing, this is sort of a common situation, R is said to be an n-ary relation on S, and in that case, we could also call it a homogeneous relation if we want to specify that that is what is going on. It's kind of a corner case, but it's also possible to talk about a relation with arity n equal to 1, in which case we call it a unary relation, and in this case we're really just talking about a subset. Finally, just so you can see some common notation, if we have a relation R on the set S and it contains elements X and Y, we can say the following three things are equivalent. X is related to Y under the relation R is the same as writing X, R, Y, and it's the same as saying the tuple X, Y is in R. And that last one sort of emphasizes the fact that R is a set, that a relation is just, again, a set of tuples. And if this particular tuple, X, comma, Y, is in the relation, then what we're really saying is just that X is related to Y by that particular relationship. So that's our definition, our terminology, and our notation. Let's make it more concrete now. We'll look at some examples. Right? So first, here is an explicit example. If we have the set L equals A, B, and C, the set contains these elements, and the set W contains the elements all, ball, bat, and cat. It contains words, right? Then we can define the binary relation R, which is the subset of this Cartesian product of L cross W, right? Such that we're defining R to contain the following tuples: A, comma, all, B, comma, ball, B, comma, bat, and C, comma, cat. So you could probably also think of a rule that would give you these same tuples, right? So this is an example of a relation, and remember this Cartesian product, what it has in it would be like every possible thing from L combined with everything from W. So it should say like A, comma, all, A, comma, ball, A, comma, bat, A, comma, cat, and then B, comma, all, B, comma, ball, B, comma, bat, etc. Right? So all of the possible pairings are in this Cartesian product, and then R is just picking out the ones that we are focusing on in this relation. Now, that was an explicit example in which we could actually write out the contents of all the sets, but we want to also be able to deal with examples where we have to use set comprehension rules to define the relation. And so let's look at one of those, right? So we have sigma. Remember, we use this often to represent an alphabet. So we've got an alphabet containing A and B, and we're going to define some set S as the union of sigma to the 0th power with sigma and sigma to the 2nd power. So we have to think back to what these powers mean, right? But actually they have a pretty intuitive interpretation. Remember, sigma to the 0th power is just going to be the set that contains the empty string. Sigma is just this set here, right? And sigma to the 2nd power is the concatenation of this set with itself. And remember, we concatenate all possible combinations, so what that's actually going to give us is every string that we can form from this alphabet from length 0 up to length 2. So that is what S is. That's what we get when we take the union of all of these different powers of sigma. Now, if you're really following, you'll say, oh, well, that's only 7 elements, and you could write this all out as an explicit set. We could. We're just doing this for practice. But so let's now define a relation using a set comprehension rule. So we're going to define this relation called R pre on S, right? And the definition is the tuple xy such that y is equal to xw for some w in S. Now, if you are the type of person who you just look at that definition and it suddenly makes sense to you the first time you see it, you are very fortunate, and you can probably stop watching the video. For everyone else, I'm going to work through it. And I hope that as I do that, it will become clear what this relation is all about. So first we want to say, okay, this relation consists of tuples xy. And what we're seeing here is this condition under which 2 elements x and y are a tuple that is included in the relation. And this condition has something to do with this equation and something to do with this w, right? We have to be able to find a w that makes this equation true, right? So we know that w has to come from S, so it would be worth writing out what S is and seeing what w's are available. And remember, since this is a homogeneous relation, right, we just have one S, our x and our y are also going to have to come from this set. So that also makes it worthwhile to write out what is in it. So remember, it's the empty string, it's A and B from our sigma, and then it's the concatenation of sigma with itself. So AA, AB, BA, and BB, and that's our whole S, right? So now our x and our y are going to have to come from that, and let's just write the equation over here. Y is equal to x w, right? So I'll just pick 2 seemingly at random values for x and y, right? So let me pick, I'll pick AA will be my y, and I'll use another color, A can be my x, right? And so now I've chosen those, and then the question is, are these 2 related, right? Do I get a tuple that would be A, comma, AA? I should keep the colors consistent. Right, is that tuple in the relation? And it is if I have some w that I can find to make this equation true. And again, to search for that w, I search through this set S, right? So all I have to do is find some element, and obviously there is one. We can just pick this same one, A, here, and use that for W2. There's no problem picking it again. And now I have an equation that says AA is equal to AA, and that's obviously true, right? So this condition is therefore satisfied, and I can say this tuple is in the relation R pre. And there's a bunch of other ones that we could kind of get really quick if we did it right. If I pretty much pick any element for y, right? If I pick, let's say, let me just pick B this time, actually. I'll pick B, right? So B is my y. And I pick the same element for x, right, I can now always pick the empty string as my w, and that's going to satisfy the relation. So I get kind of quickly can see that basically every element is going to be related to itself in this relation, right? And that's kind of a useful thing to know about a relation. We'll talk about that more later. So that gives us some things that are in the relation, but to understand it better, we should also look for some things that are not in the relation. So you can do some experimenting, but let's just pick BB as my y. I say y is equal to BB, and let's try x is equal to BA, right? And then I get my equation here, BB is equal to BAW, right? And so now you can see I'm kind of in a bind, right? Because I need to find some w, some value from this s, that if I concatenate it to the end of the string BA, it gives me the string BB, right? So it somehow has to delete this A and replace it with the B, right? And there's no string that does that. So these two things cannot be related because there is no W that exists that's going to do what I would need to satisfy that condition. So what's going on here in general? You don't always have to do this, but if you can kind of get a way of characterizing this in an intuitive English language sentence, that's often helpful, right? And so what does it mean when we write this rule? Well, what we're saying when we say x concatenated with w is equal to y, it means we're looking for something that we add to x to make it the same as y, right? And it has to come from s. But the interesting thing here is that means that x and y have to start at least with the same thing, right? If I have my y is AA and my x starts with a b, there's nothing that I can add to it that's going to make it the same as that y, right? Whereas if it starts the same way, if it starts with an A, then yeah, I can definitely find another A or find something, or at least that I have a chance. Right? I have to make sure it's in S, but I have a chance, right? So what this R pre-relation is saying is that the string X is a prefix of Y, right? And that's why we named it that way. So now that we've worked through that example, the next thing I'd like to do is show you a few ways of representing relations. And my hope is that this will help you further your understanding of what a relation is supposed to mean. So I will pick up from here in part B of this little module on relations.